Hey, John here. Let's look and see what it takes to debounce a push button connected to an FPGA.
I'd like to take a quick moment to thank all the supporters of my channel, Patreons, the people that comment and ask questions in the Discord, and likes and thumbs ups, and the commenters on YouTube. Thank you very much. You've given me all kinds of interesting ideas, inspiration, and good discussions. Thank you very much. If you'd like to be a patron, see the link in the description below on YouTube. Now let's all make sure that we understand what debouncing is. So let's say I push a button like this, a little quick press. Now look at it on my oscilloscope. This is the signal that's going into the FPGA. And this is the actual signal from the actual press that I showed you in that recording. This is really what happens. I press the button and then release it pretty quick. This is 10 milliseconds per division. So that's a quick peck, right? So 10, 20, 30, 40, 50, 60 milliseconds. So if this is me. If I did it really fast, I would be pressing this on the order of about just a little bit more than 10 times a second, which is probably all you really want to do in any sustained period of time. But in any event, you can see the switches bouncing around a lot. And by that I mean it's going on, off, on, off, on, off, on. And if you're running your FPGA and you're looking at this on a GPIO and an input, you see a 1, then you might see a 0. And if you're polling it, in a real fast loop at like 25 megahertz, which is what the crystal speed is on the board you're looking at, or, some of the other, experimenter boards could be 100 megahertz or even faster. That is not a particularly fast speed. So, what do you got? In 1 millisecond, there's 1,000 samples at 1 megahertz. So this is 10,000 at 1 megahertz and on up from there. So this is your problem, right? If you're sampling this quickly, you might see a 1, then you might see a 0, because this edge looks pretty clean here, at least at this far away vantage point. Who knows? It could go up and down a couple times in there. It certainly does go up and then back down and up again here. I don't know if that's high enough, but it certainly might look like a 1 followed by another 0, looking by a 1 and then a 0 and then a 1. This is a big problem. If you just peck this thing once and you're hooking it up to something like a counter, it might look like it counted 1, 2, 3, 4, maybe even 5, 6, 7. These might not count down there. 8, this one swings down, maybe 9, and then 10. I mean, it might look like you pushed it 10 times. And we've all seen that happen. A really garbagey bubble membrane key on, on your washer or your microwave or something when you're trying to set the time and the darn numbers go up at the wrong speed because some dingus didn't take 5 minutes to debounce that switch. Now this one in particular, electrically, have done us no favors at all. The raw switch is connected directly up to the FPGA. And by that I mean there's no capacitors or anything on the line to slow these little spikes down. I mean, you can do some work in the analog domain to clean up that signal if you really want to. I decided not to, because we can fix this to some degree in our FPGA, and that's what we're going to talk about today. Now, the worse, as this gets worse and worse and worse, you might need to clean it up in the analog side of things before it is connected to your FPGA, and put filters and things like that to get these little spikes out of here if you cannot figure out how to do it inside the FPGA. Now, there's a lot of different ways to do this. There's probably as many ways to do this as there are buttons connected up to FPGAs. So, as always, I don't know everything, and I'm just one guy with one opinion. And in fact, today we're going to look around the web. I did some Googling, and I found a pretty decent write-up on this topic. And I think what we could do is sort of look and see what they were up to, because they post a couple of interesting ideas, and by this I mean this page right here. I'll put a link to this below in the description on YouTube. So somebody asks a question, I put the circuit together, it stinks, and here's my Verilog code, and blah, 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 and I do some simulation, and it doesn't work, yada, yada, yada. Okay, we don't have to worry about what's wrong with that one. Somebody else puts a post back in here that basically is, let's just throw away your idea and start from first principles and look at this design instead. Now, this implementation is interesting for a couple of reasons. I thought it would be good at this point to go through this and see what's going on. I mean, this is just, somebody's opinion, but it's not a particularly bad one. Let's look and see what we got in here. Because, I mean, debouncing a circuit is a very common thing that you need to do. And everybody, like I said, you're going to have a bunch of these out there. Let's look at some of the features that this guy did here and assess whether they're applicable to what we want and or other circuits that you might have and whether you can use this thing. Now, we already talked about a synchronizer. What they did is they hooked their push button up to a synchronizer first because they don't want any metastability problems on the way in. It's bad enough that the signal's bouncing up and down like crazy and could look like multiple ones and zeros following each other. You don't want to, on top of that, have metastability problems. Now, I have a synchronizer that I've already implemented. We all have our favorite one. All of them work the exact same way. This is why they probably don't even have copyrights or anything on here. These are just very, very generic, very standard circuits. You can see there's a shift register in here, and every time the clock ticks, he's got 3 here, and basically he's going to serially take the input bit. What is he doing? He's putting in the least significant bit and concatenating it with the prior 2 bits in a shift register, and every time the clock ticks, he just shifts it left. The one I did shifts it right, and we put it in on the right. It doesn't matter. You're going to see one of these 2 styles and a couple of different ways of expressing what you want in Verilog if you look around. So this is nice to see a variation of this. But let's look strictly at the debouncer and the test bench that this person has. Now, I've taken the liberty of pasting this into a file here on my Raspberry Pi. Let's take a look at the land here. This is these Verilog examples. There'll be a link to this in the GitHub repo that has all these files in the description below on YouTube. I've got a library. I'm starting to put together this library, and right now I've got a synchronizer in here and a debouncer. Let's go ahead and look at my synchronizer since we're here. So in here, you're going to see basically the same thing. What do I got here? See the sunburst designs? Yeah, our guy, Cummings, I've mentioned this guy's papers before. This is not a bad resource. Very good opinions and ideas in here. There's another YouTube video. That's my YouTube video from last time that I posted in here. Look at the input is connected to in, the output's on out, and you've got clock. And here's how many shifts bits are in their shift register. You'll see this is very similar to the one you just saw, and mine goes in on the left and shifts it to the right. The other one goes the other way around, and the output on mine is always the least significant bit, or the other one would have been the most significant, whatever. These are always the same thing. The key here is it's called sync. We've got a length equal 2 by default. We can override it with a bigger number if we want. And we've got in, out, and clock. So when you want to instantiate it, that's what you need to tend to those values. All right? Let's look at the test bench first. I stole the test bench. This is the one you were just looking at. This is the link, again, in the description below the video on YouTube. What do we got in here? I changed theirs to the one that I've got. Oh, you get lowercase instead of an uppercase. And they used 3 for the number of bits. And the reason I made mine match theirs is because if you go over here to this web page and you scroll down, they have this is what you're going to see from the test bench kind of screen capture here. And in order for it to act exactly this way, you have to have the same number of bits in your synchronizer. So here's the synchronizer. It's got the clock, the in, and the out, okay? So schematically, what you're doing here, let's put this back on here. This one is an interesting implementation of a debouncing circuit. We're replacing this, okay? But here's the synchronizer. You got the switch coming in, the same clock, collects them both. There's your shift register. They did something interesting here, looking for edges. This approach did not work for this person, so that's what we're throwing out. But basically, you've got this shift register followed by go somewhere and process something. So what we're doing is sitting over here to the right of that shift register. And of course, ours has 3 because we said 3 rather than 2. Now here's the debounce instantiation. Notice we set max count to 4. This will make more sense in a minute. We send in a clock. We've got the input, and we've got the output. So what we're going to do is we're going to take our noisy signal. We're going to take this thing, and what we want it to do is go down, stay down, and then go up when it's done. We need this to be clean and square and synchronized to the clock domain of any circuit that's processing this signal that comes out of our debouncing circuit, okay? So that's what's supposed to happen in here. We're going to take it. It's synchronized already on the way in. This button sync is the output up here, as you can see from the synchronizer, right? The output of the shift register. And the output is going to be called button sync DB for debounced. Now this one of the interesting things about this is they generate an edge pulse, a rise pulse, and a fall pulse. Sometimes you want to have the square wave cleaned up signal from your button. That would be this. Sometimes you just want to know, was the button pressed or released? In other words, did it change? That'll be a pulse on here. This one here will pulse once and only for the period of 1 clock cycle period, right? One time pulse that it went from 0 to a 1. This will pulse that output. And this one here will say a single clock period long pulse when it goes from a 1 to a 0. And these are pretty cool to have, all right? And you'll be able to see if everything works really nice and cleanly on the output of the test bench. So what does this thing do? It's going to say, I put this in here. They use a different simulator that they don't have to do all this stuff, but I put it in because we're using Icarus, right? So we create our dump file. We say dump everything, and they start with their clock as a 0. And this is one. Remember that every 5 clock ticks, they invert their clock. Okay, that's one every 5 time periods, I should say. Okay, and the reason you want to keep this in mind, and the reason they made it bigger than 1, was because it makes this down here more convenient. They start off by waiting 2 simulation clock periods, and they set the button to 0. And then all these other ones you'll see are a multiple of 5. Okay, and the usefulness of this is to kind of show you that the button never really will change on the rising edge of your system clock. Okay, this is not the best test bench. You probably should put some cases in here where it does co-align with this to make sure that doesn't do anything weird, and move it around a little bit, jitter it around a little bit to make it more realistic. But the bottom line is it'll either move exactly at the same time there's a sensitive edge on your system clock, or it won't. And that basically, in this case, is more of an issue with your synchronizer than anything else. And we talked about that before. I'll put the link to a playlist of all the FPGA videos on my channel that I've recorded. You can go back and watch this if you didn't see it or don't know what these things are, okay? So that really is more related to that thing than the debouncing, okay? So what does he do? He's waiting 20, and then he goes to 1. He waits 20, goes to 0, 22. So he's moving around a little bit. And he goes to 1, and then he stays 1 and goes 0, and then a 1 and a 1. He's going 1s and 0s and 1s and 0s and kind of quasi jumping around a little bit in time. And then they finish. Now, I didn't change these times, again, so it matches the diagram in the web page. So if you want to go read that, at least you're in sync with what that looks like, at least at this point in the game. I may add some more code down here to try some other cases if we want to. All right, so that's the big picture here. We got a button that comes into our FPGA, and it's noisy like this. It's synchronized to our local clock domain by simply delaying it so that if it moves at the right time relative to our local system clock. We've got a debounce circuit that has this parameter, I'll explain in a minute, that has the system clock running at whatever the system clock speed is, which is the same clock and in phase with the clock that's running our synchronizer. And we run the button through it, and hopefully we get a cleaned up square wave coming out here, okay? Let's have a look-see at the big picture here. Okay, here's the headliner. The first thing we notice is max count, and we overrode that to 4, recall, in the test bench when we instantiate this. And there's the usual inputs and outputs. Now, I don't normally put regs in my input and output ports. This design does. So this is number 1. Here's a variation, another style of implementing some code. So you're not going to only see my particular style when I walk through other people's code, which is a good thing. Variety, right? Okay, so the switch signal comes in here that is already synchronized to the local clock domain. The debounced output will come out here. This thing will pulse 1 clock cycle wide high if the output is changing from a 0 to a 1 or a 1 to a 0, and these two here will single pulse for 1 clock cycle. A lot of times that's called a tick. Certainly Pong Shu likes to call those ticks in his book. I mentioned that before on my channel here. This is a rise tick and a fall tick output signal in his terminology. It's 1 cycle wide, just like the edge signal over here. But it'll only go high for 1 single cycle when it goes from 0 to 1 or a 1 to a 0. Okay? And we get down to the implementation. You've seen C-Log2 on my channel before. This is the number of bits you need if you want to count up to that number there. And that's how many bits we need in a counter. So what we're going to do is we're going to build a counter. All right? Big picture, big picture. What this is going to do is it's going to use the counter you just saw. To say, look, if I see this change, and it stays changed at that new signal for as many clock ticks as that counter is set to max count, then and only then will I assume that the signal has become what it changed to. So in this case, it would go from a 1 to a 0, and as long as it stays 0 for max count number of clock ticks, and remember, I'm running at 25 megahertz. That's not a very long time given this scale, but for testing, we don't want to have, several million clock cycles. It would take 4 hours to run the simulation and be difficult to plot. All right, I'm just saying. So there's an artificially slow amount or a fast amount of time, however you want to think about it, or maybe it's just a really slow running clock, relatively speaking. Okay, so what we're going to do is we're going to see if it changes and it stays changed for whatever the max count is, and you saw on the test bench it's 4. And it doesn't whipsaw back and forth like it does in here. Say, oh, it changed. But has it changed for 4? Oh, no, it changed again. Okay, it's going to reset its counter. It says you can change, but you need to stay there for a little while before I will consider the fact that you really have changed. And if you think about it, if the signal does this and it goes 1, 0, 1, 0, 1, 0, and it's bouncing back and forth, could do this for an hour and a half. And you're not going to know anything on the output signal of this module because of the way this particular debounce circuit is implemented, all right? Now, it depends on your needs, right? You may not want that, but that's why you have all these different types of debouncing circuits. For a human button press type of thing, this is very common style. You see it change, make sure it stays stable for a little while before you say, okay, it looks good to me. I'll now proceed, propagate that signal to the rest of my circuit. Now, this is a really tough one to clean up, by the way, because this is a pretty long time, relatively speaking, with a 10 millisecond time division there. That's almost 10 milliseconds. It changes back for almost, 15 here, almost 10, certainly more than 10, and then it's going really fast. These high-frequency ones are going to be easy to get rid of. And things like this that are relatively small are not too hard either. You just simply set your count time big enough to span what you consider to be your worst-case scenario. This one is really bad, by the way. We're going to have to set it to like 20 milliseconds to not falsely trigger here and to not falsely trigger, up and then down again over here. So if we do this, think about this, right? Wait for 20 milliseconds and make sure you're stable. Oh, I went astable. I'm not stable anymore. Okay, reset over to here. Now I'm back to where I was. And when that happens, we're going to just reset our whole logic. We're going to say, well, that must have just been a weird, a lightning strike down the road or something that caused a little spike. We won't see this at all in our output. Okay, it'll go back to where it was. Everything will be copacetic. We'll sit down and we won't do anything. Then it'll change again. It'll go from 1 to 0. It'll go, aha, it's changed, but it's bouncing back and up. Well, no, okay, we're going to not care about that. It'll come back up here. Oh, it changed again. Okay, it's going to start counting every time it thinks the new signal is not what it is currently reporting as its output. Okay, so if its output is currently 1, which is the case here, right? Maybe I should open with that, but yeah. The input and the output are both 1 here. The input changes to a 0. The output will stay a 1 until the counter expires. If it whipsaws back up here, it'll go, oh, that was just a false alarm. It resets itself and it stays 1, no harm, no foul. This will be completely thrown away, as will all these spikes. Oh, it went 0, but not long enough. It went back to 1. Okay. Oh, it went to 0. Okay, start over again. And it'll bounce back and forth and back and forth and back and forth. And finally down here, it'll say, aha, it has gone to 0. It has stayed 0 for an acceptably long period of time. And maybe way over here will be the point in time where we actually see, okay, bang. This is when it went from 1 to 0 on the output of our synchronizer. And the same thing will happen over here. It'll jump around and it'll go 1 and it'll, well, I don't know, we better wait a little while, aha. And then way over here, it'll count up enough to say it has gone from the 0 to a 1 and stayed there long enough for me to accept that that is the case. And that's how we're going to debounce this thing. All right. Whether you do that with resistors and capacitors and charging things up with op amps and Schmidt triggers and stuff, basically it's the same thing. All right. So you're wasting time by either charging up an analog component or you're counting out time and you're doing it digitally. You end up in the same sort of results. All right, so let's see how this thing works. That's what the counter is all about here. There's the number of bits we need to count up this far, which we've set to 4, like I said earlier. So this counter is going to go from 0 to 3, okay? As we'll see, it counts up to count minus 1 because it starts at 0, right? Okay, so there's our counter. These are the wires that are going to come out of our combinational logic that we're going to use to say, these wires are going to say we do have an edge provided that some other conditions are true, and you'll see that down here in a minute. So that's what these are, some internal connections between some combinational gates. We've got an initial block in here, which is useful on FPGAs, not on ASICs. It just simply sets the initial values of some reg variables, the counter and the output, which is this guy here, and the output reg up here. Let's look at the code here. We start out with 0 when the FPGA starts up. This doesn't actually have a reset signal in it at all, which is maybe not the greatest thing, but probably okay, because we're just debouncing a switch, and this will happen without any reset logic, which would mean that the switch with debouncing logic runs all the time, whether the FPGA is in reset or not. Quite often you do want to see a reset signal come in, even if it's some trivial little thing here that doesn't really have a huge impact on everything else. And the reason you would do that is because you would want any simulation to be perfectly reproducible, no matter what the current input value is at the point in time the rest of your circuit got reset. Okay, so then this would always start up in the same way. As it is right now, this is not resettable unless you reboot the whole FPGA. All right, just a little side note. I don't care, and it's not a big deal, but it could be if you're in a large project. It's not the best style, is my point, to create these modules that cannot be reset along with the rest of your circuit. Okay. What is this thing going to do? Every time we get a positive edge on the clock, now we're looking at, what do we got here? We got the mixed bag of your combinational and sequential logic all in one big always block, which is a style, okay? Not one that I normally use. So far, I've been separating the sequential logic from the combinational logic when I build a state machine. So this is all wadded together in here. In some ways, this is easier to read because it's all on one screen. In other ways, it could be subtle and might not be as easy to understand when it's explicitly broken into two pieces and rammed in your face. Okay? So let's look and see what's going on here. Every time there's a rising edge of the clock, this always block will be logically processed, which means all these will be set to 0 unless later on they're overridden and given other values down here. Okay? So what does he got here? Freeze the counter to reduce switching losses. I wouldn't have used this word. The motive to do this, by the way, is we will see what he's going to do is, when I was talking about, let's start counting a delay when we see something change and say, if it stays changed long enough without it whipsawing back and forth like this, we'll just assume we're good and propagate that out at that time. What this note is referring to is, should this counter tick and advance and increase in value all the time on every clock edge or not? And the answer they chose is no. And the value is that what it does, if the counter doesn't go, is not doing anything when it doesn't need to do anything, what you're doing is reducing the switching power consumption. So the losses that they're talking about here is in wasted energy and potentially EMF noise and stuff inside the FPGA. Why let all these gates and stuff chatter if they don't need to? This is a good idea, in my opinion. Okay, so by the way, simply stopping counters and other logic from changing their states when they are a part of a circuit that's not in use or not necessary to change their states, because the rest of the circuit's doing something else or whatever, is the number one most significant way to reduce power unless you're going to redesign the actual silicon. That is the best way to cut your power consumption, let's say on an existing silicon die design, okay? And this is why all these microcontrollers and system on chips and stuff like that have these horrifically complicated and unbelievably annoying, in many cases, phase lock loops and clock system generators and multiple speed clocks for high speed and low speed and all this crazy stuff. And the reason they do that is for battery powered circuits and stuff like that. Sorry, again, another digression, but that's what they're referring to here. And that's, like I said, a pretty good idea. Okay, so you're going to zero everything out unless otherwise manipulated down here. So this is the entire debounce logic hiding right in here. So what do we got here? When we first come online, the counter set to 0, and we ask, does the current counter equals max count minus 1? Now you might say I just set it to 0, but not, because this, remember how this thing works. The non-blocking assignment will not update the counter register until after this always block is fully completed. So asking about its current value here gives you the value before this will have completed. Okay? Again, another reason we want to look at somebody else's code so we can understand these things. This is a great learning exercise. I would not use this style. This is why you take your sequential and your combinational and put it in two different sections. That's a little easier, in my opinion, to understand if you're first getting started. But that's what's going on here. Don't let it confuse you. So if the counter has counted up to max count minus 1, which means it has already gotten to the point, due to the logic down here, you'll see in a minute, that max count time has passed since the last time it saw an edge on the input. Okay, when that happens, that's when you're saying, okay, I'm going to commit and say this is the new output signal. In this case, it would have gone from 0 to a 1, weighted max count number of clock ticks, and said it hasn't moved, therefore let's update our output. And then over here, it will not do it until like over here. Okay, if you tune all this right, you'll see that no matter what we do, this can always happen, and this gap can always be bigger than whatever you've tuned it to. You can't do this perfectly. It just can't be done, right? Because a switch is a mechanical thing, and people's hands quiver and move, and they bounce, literally physically bounce, or they don't press it right, or they're grinding it and rocking it back and forth, and a little bit of a glitch might sneak its way through, and it might be longer than whatever you set the time to. I suppose if you set it to like 3 seconds, which would be the most annoying button on earth, by the way, then maybe it would not be so susceptible to noise. But these are all these tunable things. You know, it needs to be useful, sane, and reasonable, and not too bad when we're done with it. Okay, so ultimately, it's a best effort sort of thing. So what happens when max count time has passed since the last time it changed? And we'll see the changing happen down here. If it has been stable that long, what do we do? Well, this is the point in time when we take the input value and we propagate it over to the output. It's been stable long enough. That's when we propagate through. And we know we're changing it because of the logic down here. We're going to say, this is the point in time where we do the single tick advertising of whether, first of all, this always goes true for one tick whenever the value changes, 1 to 0, 0 to 1. This one says it went from 0 to 1. This one says it went from 1 to 0. All right? So if the counter is not yet at max, which means you either just reset it or it has been as we'll see in a minute, the output value is not equal to the input, okay, because we're applying what's called, temporal hysteresis. You Google it. I got enough digressions in this video if you don't know what hysteresis means. If the output and the input are not equal, and that's the case when we're sitting here and we say, well, the input has changed up to here, but that max count period of time is not yet passed, the current output is still 0, even though the input is a 1. That's what this is detecting here. So if the output and the input are not the same, this is when we advance our counter. And they comment over here, we only increment when they're different, which is why over here it's always frozen when they're the same, because this is the only time we ever change the counter variable. All right, so this is you sit and think about it a little bit, work this through if it's not immediately obvious what's happening. You might want to start by looking at this, then this, then this, and this in that order, because when you first look at this thing, that kind of helped me. It's kind of a bottom-up what's going on here, because this is when it's changing, it's counting, it's waiting, right? Well, what do you do when you're done waiting? Well, that's when this becomes true, and you do this, okay? And this is the stuff that normally you would see in part of your combinational circuit if you factored this out into 2 separate always blocks, okay? Now down here we say what? W edge, I assume this prefix W in what we would call Hungarian notation. In computer science, go ahead and Google that when there's a prefix of what it is. That's what they call that. These are wires called edge, rise, and fall. Now, these are not the outputs. Okay? So when you have an XOR between two things, it's true whenever they're not the same value. So whenever the input and output are different, that's when this is true. And this could be true a lot and for many ticks in a row, many clock periods in a row. It is only propagated to the output for a single duration of 1 clock tick right here. Okay? That's why it's only 1, even though this one could be true for several ticks in a row. Rise kind of works the same way. Whenever the in is high and the output is low, we know if we come through here at that point in time, that we have a rising edge. So this could actually be true several clock periods in a row, and not until we get in here does it go propagate it to the output for one and only one time. And the same thing with falling edge, it's just the other way around. Now you might ask, how does, if these are true for several clock periods, how come this only goes out for one? If we stop the clock when this is not, be careful here. Look what's happening. All these are set to 0 unless they're changed in here. Okay? So, the counter, when the counter equals max count minus 1, this will execute one time, and we know that this is not true, because the last time the clock ticked, it had to go through here in order to advance the counter for the counter to become max count minus 1. Therefore, we know the counter is not 0. It could become 0. In fact, it will become 0 when this is true, and we do this, because this is in an else block, and the counter will not be modified in this particular execution of this always block. So when this always block completes, these will end up propagating out. The counter will have been left set to 0. Okay? So the next time the clock ticks, this will not be true anymore. And if we've debounced it, we know that the output and input are the same value, so this won't happen either. So all that'll happen is every time the clock ticks, all these things will just be set to 0, which they would 99.9999% of the time. That's all this block will ever do. Okay? This only happens once every time you're either going, pressing the button down or releasing it. And this only happens a couple of, however big the counter max value is, while it's trying to throw away all the high frequency noise around a button press. Okay, so that's how this whole thing works. Let's go ahead and run the simulation. Let's see what they got here. This is the same timing numbers that they give you in that web posting. So let's see, let me open this thing up. Here we go in here. Let's look at the top level stuff on the test bench, because that'll show us our button. The button, what do we got here? Button sync, button TB. Okay, what we've got here, this represents the raw button coming in, which is the super noisy thing. This represents the synchronized to our local clock domain signal, okay, which will be delayed by the shift register that is the synchronizer. And this is the output from the Debouncer, our free running clock. And then we've got the 3 edge, fall, and rise tick signals from the debounce circuit as well. Let's go ahead and bring all that up, put it on the screen. Let's kind of try and make it fit as well as we can. Let's not add any other stuff just yet. There's your raw button. Let's turn on our highlights. We can see what's going on. So here's the button going on and off over the course of time. We've got undefined stuff here because they don't have a reset signal in this thing. And funny, how do you have a reset signal, which is a push button that needs to reset the reset debouncer? Okay, you might have a chicken and egg thing here. So at least one button in your design will probably not be resettable, and that'll be the reset button itself. All right, I'm just saying. And that's okay, actually. All right, so the button goes on and off at times that are not necessarily synchronized to the clock. Let's reorganize this a little bit. Button sync and the debounce one here. So there's the clock. It's running. Okay, here's the button, and you can see this edge. If we zoom in, a little bit here, you can see it going up and down. It's not aligned with the system clock. It's a little out of phase, which is fine. That's what you really want to do to show the difference between the raw button. Oop, come on, where's this little edge here? The raw button input, which is, a 1 here, and the synchronized version of the button, which is simply a shift register that's delayed, right? And it's delayed by 3 because that's what our parameters said. And if we look at these edges here, every rising edge is when that shift register runs in the synchronizer. So the button's a 1 there. It sees it. It propagates it to the second latch in the synchronizer, and over here it's coming into the third latch and comes out. So there's our synchronized button press, and it's delayed by 3 clock periods. Okay. Now, this button went from a 0 to a 1. Let's have a look-see at our debouncer here. Let's look at the counter inside our debouncer, because you'll see it going. I think if you double-click this, it adds it to the screen. That's nice. What else do we want to see over there? I guess we don't... Well, we could put these. Those are the wires that have these, edge, fall, and raise that you can see are multiple clock periods long. And then over here you can see the outputs that are assigned in that always block when the counter reaches its maximum value. So we can see it happening right here. This is the output of the synchronized button. And you'll notice it doesn't go from 0 to a 1 until way over here, when in reality, you may have pressed the button here, and all these clock cycles later go by before this counter and the synchronizer do its thing and gets to the point where enough clocks have passed with the input, which is this guy right here, has been stable long enough to be considered reasonable, and that we would output it over here. Okay? So notice you got glitches here, and they're like not even close. Why? Because it's the synchronized input that's going into your debounce circuit. Okay? This is a pipeline. All right? This is going to, when I first started working these, even today, it can get very confusing. What the heck's going on? When did something happen, and at what point does it actually manifest itself in some recognizable way? So here's what's going on. The synchronizer went from 0 to 1 here, and that's our input to our debouncer, okay? So the debouncer doesn't see it. In fact, it doesn't see it here either. It doesn't see it until this rising edge. It has to be 1, and then we need to see a rising edge inside our synchronizer logic. That's why you see over here this counter going from 0 to a 1. Remember the logic in there. This counter will advance if and only if the output and the input are different, and they are, because button sync is the output and it's 0. And the button input to the debouncer is here, and it's a 1. So that is the first point in time we see a rising edge of the clock, and the always block runs, and it'll advance the counter from 0 to 1. Okay, and we want to count up to 4 minus 1, because 0 counts as one of the values. 0, 1, 2, 3, and then we have an output, and you can see there's a 3 right there, okay, in binary. All right, so he's high. We got a rising edge. Great. Let's move on. Over here, another rising edge on the clock is true, and it sees that input as a 1. He advances it to a 2. The next clock tick that comes along up here, the output and the input are no longer different. This is the input to the debouncer. The output is this guy right below it. They're both 0. What happens when they're the same? Both of the cases of the if block are false. Therefore, the default logic at the beginning, let me background this and rerun our editor and have a look-see. What happens is we're in here. The counter is not max count minus 1, which is 3. They're not different anymore, so I can't advance the counter. Therefore, the counter will go back to 0 and stay there. This is how this particular design of the debouncer works. Okay? So because the output and the input are the same, we reset our counter to 0. That's why you see the 0 right there. All right? Then the input on this leading edge is 0, and because this is synchronized, what it sees is the 0. The setup time over here is what you need to look at when you have this leading edge. What is the value on the input, right? It's low when that leading edge is in there. Then after that, it is a 1. All right? Now, we don't, this particular simulation doesn't show propagation delays. Fancier ones do, and I think this one can if we get really cute about it and tell it, oh, this has a 5 nanosecond propagation delay, and you zoom in a lot and you'd see this goes up, then the one down there would go up as a response to that. Or there'd be a cause-effect arrow in here if you drew this out in a diagram, for a data sheet or something like that. Point is, you're looking at just to the left of the rising edge to see what this thing is and what it means to the circuit. Okay, so it's 0 again, so this thing stays 0 is my point. This leading edge, we got a 1 on the input, a 0 on the output. They're different, and we're not at the max because it's currently 0, so we advance the counter to a 1. Same thing here. The input's a 1, the output's a 0. They're different and not at the max. We advance the counter, we go to 2. We got another 1 on there, and we're now advancing to 3. And the internal logic is now that is the limit. It is max count minus 1. So the next time there's a clock tick, which is right here, what will happen, and they're still different and so on. Actually, I take that back. It doesn't matter that they're different. What we have is we have counter equals max count minus 1. And in this particular case, we don't care whether they're the same or not. You should have put a test case together, and maybe we'll tweak it. This video is getting long. I won't do that. I'll leave it as a test to the viewer. If you lower your input signal here, like over here, this will still output this because the logic doesn't care that it has gone away at this particular point in time. It has been high long enough. This thing got to 3, and we have a rising edge on our clock because it checks the value of the count before it cares about the input, okay? That's why we got an else in here. And we don't get here when this is true, is my point. It won't be until the next time the clock ticks that it'll want to check down here again, all right? I'm just saying. So what else do we got going on here? We're at that point in time. Therefore, we have a rising edge. We have an edge period, right? So the output that says an edge change has occurred, and that's what comes from here. It says an edge change will occur. What this signal down here means, an edge change will occur if we get to the maximum count, which happens here. When you're at the maximum count, and then we have the rising edge, we then propagate for one period the edge signal here, okay? And because it went from 0 to a 1, we output the rise and not the fall. And because we've done all that, we're not going to advance the clock, right? The counter here, that we don't sign it at count value, therefore the default kicks in. And the counter will go to 0 along with all these things changing or being assigned for that one period of time. So that's what's going on here. And the same thing will work in the opposite direction. From 0 to a 1 or a 1 to a 0, that's what you see over here. So the, what is this? Here's the synchronized output. Here's the input. So what's happening in here? He's gone from 0 to 1 long enough to propagate through, and from the output to become a 1 right here, okay? And now he goes back to 0 on the input, but not long enough for the counter to count up to the 3, right? You can see it going, it's 0, 1, 2, and then it notices that the thing, it's a whipsaw, and it went back high. So this little glitch right there is ignored. Counter goes back to 0, and it wants to wait until it gets all the way up to 3 here, while the input is 0, and it's not till over here that the input's low long enough for it to be recognized as being acceptable. And then you see the output go 1 to 0 there, and a single tick cycle that says it just went low here, and so on. So there's your raw input, there's your synchronized input here, which is basically the same thing, but time aligned to the clock and delayed a little bit, okay? Then you've got your debounced output, which is delayed as many as your max count number of clock cycles off of this edge here, so that it can ignore these little short periods. This one here and this one here are ignored because they're not long enough to be considered valid and part of the new state when you're pressing your button. That's how you get rid of all these little glitches in here. Okay? Now, that's the whole ball game, and the only thing you really need to do now is make sure that you have a decent value that you choose when you use this to put in here for your max count. All right? Now, let's look at this thing for a minute. here's the situation I have. And if I use the raw clock that's on my FPGA board, if you watch my channel, you'd know that's 25 megahertz. You can put whatever clock you want on yours or whatever experimenter board you have. You got a clock that runs at some rate. If you put your oscilloscope on here like I did, and you watch this, now you're going to you can create impossible things that are just too long and just too outrageous. And eventually you got to just say, if the guy's going to hammer the switch with a, with a hammer or a screwdriver or something like that, and it's going to do weird things as a result of that, I'm not going to deal with that guy. Okay? The heck with that person, right? But in a normal case, you got these little glitches that look like this. We need to pick a time. Now, this one's tough. This really is tough because it went down, stayed really clean, low, and then it went up and stayed clean, high. This one might actually be, unless you set it to like 15 milliseconds, which is reasonable, I suppose. You can't ignore this thing because it lasted too long. There'll always be, just a little bit longer, right? But this is how you decide what you want to do. It really depends on the switch you chose, the voltages, and all your circuits, and whether your user has got, some serious problems when it comes to pressing buttons or not. Okay? So I got a couple of other screen captures in here that I've also did while hitting the button. What's my time scale on this one? 1 millisecond per period. This one's not too bad because the previous one was 10 milliseconds, right? So what are we looking at? This is just a little bit more than 1. 1, 2, 3, 4, 5, 6, 7 maybe. So this is actually only 10 milliseconds from the first hint of, in this case, me releasing the button. Because on my board, what happens is when I press it, it goes low, and when I release it, a pull-up resistor pulls it back up high. Okay, so as I release my button, it's kind of bouncing. It's literally bouncing. The contacts are bouncing in here, and so if I set it to 10 milliseconds, this would be clean. It would ignore all this, and it's not till here plus 10 milliseconds later where it'll say I've saw it go high and stay high and stable for 10 milliseconds, and then it will change the output from the debounce circuit. That's not too bad. This is your best scenario. One of the times I pressed it, it was really clean. If you look in here really close, though, it might have a little bit of a whipsaw in there. What is the signal on 1 millisecond scale? So this one is nice, It'd be nice if all switches were this great. Then we just simply set it to 1 millisecond, which in this case is an enormous amount of time, but not too bad for human finger speed, right? And then you'd be fine. Here's another one that's looking like about a 1 millisecond. What's this one? Here's one where we've got 100 micro. So yeah, that's probably me zooming in on the previous one by 10 to 1. This one is really nice because, again, if it's a human speed button press, all you need to do, 1 millisecond, is this whole, almost the whole screen. This is just over 1 millisecond for the whole screen. And that'll be perfectly reasonable. In terms of how much time I need to waste when debouncing, okay? So what do we got here? This one's got a little bit of noise on about 100 microseconds. Again, 1 millisecond is like the whole screen, so this is not a problem at all. And then what is this one over here? 100 microseconds again, 1 or 2 milliseconds. 1 millisecond is the whole screen again. It'll get rid of all that, okay? And by measuring these things and assessing the time, what do we got on here? This is 100 mics. Yeah, again, not a problem. Even if these are noticeable by the FPGA, that doesn't move enough for me to think that it would even think that that was going back to 0 again or not. But it might be that the scope at this scale can't show me. It may not have detected. Maybe this does get way down and then ping back up. I don't know if that's a thing or not. Here's a really nasty looking one. This is one situation that could cause some serious metastability in your circuit. Okay. By it literally being in the middle, so you don't know if it's a 1 or a 0, and the clock is going to tick a bunch of times. It may very well be that this could go metastable. And this is why we do a synchronization in our circuit. Normally, you think of it in terms of the setup and hold time, but the setup and hold time is by definition violated already anyway. If you got high frequency noise, especially in the illegal area of your input voltage, this is really bad. Okay, so your synchronizer will help get rid of that noise as well. Again, that was a pretty high frequency. We're only at 100 microseconds here, so again, well, maybe 1 or 2 milliseconds of time would be good enough. Now, I measure this and I count it out in time because you need to figure out what goes in here. And what goes in there is going to be dependent on your clock frequency. And this is a simulation, so you can set this frequency to whatever you want. But in my case, it would be 25 megahertz. So in order to synchronize this, if I wanted 1 millisecond, what would we have there, right? So 25 megahertz is this. 1, 2, 3, 4, 5, 6 zeros. And if you divide it by, 1,000, you would need to count this many ticks of the clock to represent 1 millisecond. That's a pretty big number. So your clock is going to, your counter is going to have what, 15 bits in it to count that high? That's 15 lots. And so you got to be careful. You know, if you have a whole bunch of push buttons in your circuit, and each one of them has a debouncer on it, you're probably going to need a debouncer on every one, and each one of them has 15 bits of count. That's the max count. If you needed to, that's in the, let's create the test bench here. If you wanted it to go out that high, you would need to count this to 25,000, which is insanely big, right? So in this scenario, you'd have to multiply all these by some giant number, is my point. But I'm going to go ahead and run it like this anyway. It won't even detect that it has changed, because it'll never get that far in this simulation. But what we can see if we do this, if we open up the debouncer, look at how many bits is in our counter. All right, so we end up with a 15-bit, 0 to 14. That's 15 lots just for one debouncer. If you got a dozen, 10 push buttons connected up to this thing, that's, 150 LUTs just for the counters, plus all the other LUTs to do the rest of the work for the debouncer. So these aren't exactly free, is my point. And if you design a circuit that has more than one clock running in it, and that's not terribly uncommon, you get more of a sophisticated design going, you might have more than one clock running at the same time. And if you phase lock all these clocks, they can be considered in the same clock domain. In other words, as long as each one of the system clocks, when they change, they all go together, or they're adjusted accordingly so that they're out of phase in a way where they never can be in violation of the setup and hold time, then you're fine. In case it's lost on you, the value of that would be you could use a slower running clock to deal with your keyboard debouncing and not use tons of LUTs and all your counters over there, while you're using a high-speed clock to run the rest of your circuitry. All right? So that's a little bit more advanced topic, but you might run into it when you're poking around on the internet. You could, if you think about it, even if you don't synchronize those clocks together and you got a fast one and a slow one, you simply could take the output of your debounced push button and then you could synchronize it with another synchronizer between the debouncer and whatever clock domain you're going to send the debounced output of your push button. So what am I getting at here? So sometimes you have synchronizers inside between two of your own circuits that cross clock domains. They aren't, in other words, they're not just used to bring in signals from the output, from the outside world on the pins of your FPGA. So the value, of course, would be if your synchronizer uses less LUTs than the counter that you need to do your debouncing, then maybe you'll be ahead of the game. So if you start running out of FPGA resources because you've got a lot going on and there's a lot of buttons and a lot of circuitry and stuff like that, that's the sort of thing you need to start thinking of. Now, let's get a little bit more advanced from where we're at right now in this particular series. But I want just plant that seed because it can come back to bite us, and you don't want to get all upset that you got 7,000 LUTs and they're all burned up in your stupid key debouncers. Be creative, right? Slow down a clock and run that stuff in a different clock domain. Maybe it'll only need to run at 1 kilohertz. That way, one single clock tick is an entire millisecond. So the number of bits in your counters become much less, is my point. All right? So that's what you do for debouncers. That's a particular style that you saw on this particular web page from this particular person who posted it. And the interesting things in here are that they included this tick logic that's going on in here that you see in their little example output. We just saw all this stuff. These are the tick up, tick down, or rising, falling, we should say, outputs that you might want to use in your circuit. Now, there's one last tidbit. The other thing that I wanted to mention as a result of this style of code design, they're outputting, there's their synchronizer, they're outputting all these extra signals down here beyond what you might think you would normally want. I just want the thing debounced, I don't want all this other stuff, and now if I'm a big tirade about wasting LUTs and so on, we now are generating all these other signals, and I'm wasting stuff, so maybe I'm going to take this debouncer and delete all this code because I don't want it. No, don't do that, okay? Leave it in there. What happens is, if you have a thing like this and you want to create a general purpose library module out of it, and it's got extra outputs on here, if you don't use these outputs, the synthesis tool, the compiler, will detect the fact that that goes nowhere and is used for nothing. Therefore, when it's building the circuitry down here that generates it over here, what does it do? It generates it there. Yes. And then it propagates it over here with latches and wires and gates and all these lots. It will backtrack. Okay? It'll say no one used this. Therefore, no one's using this. Therefore, no one's using this. Therefore, I don't have to calculate this XOR operation between the input and output, and all that circuitry will be thrown away and not waste any LUTs at all. Same with these, same with these. So if you don't use any of this stuff, that circuitry won't exist in your FPGA anyhow. In fact, if you only use maybe the rising edge in your circuitry design, maybe all you want to know is this: was the button pressed? And all the other time, I don't care. You just want one clock tick trigger for some reason, and this is the only thing you use. The same logic will kick in. It doesn't need that, throws it away. Doesn't need that, throws it away. It also doesn't need the logic to route this signal back through to the output either. Okay? All the unnecessary stuff is eliminated and thrown away. Okay, so that is the other tidbit here. Make a nice general purpose library like this so that you have this if you need it. Don't waste your time optimizing. The compiler's not stupid. If you're not going to use this signal, it knows to go and throw away everything that ever generated it all the way back to whatever inputs are still in use for some other reason. And you save all those LUTs, okay? So this is a nice flexible thing. It actually works pretty well for most generic cases. One last thought, I guess, on why you might not want to use this is it's symmetric. All right? The counter counts when you are measuring the should I become zero. And once it stabilizes, and the input the input catches up with the counter and it's stable for long enough, and the output is then changed. It may be that the nature of your circuit that generates this noise is asymmetric, is my point. It might be that in a falling edge, you don't want to wait as long as later on a rising edge, maybe. They'll all depend on your specific situation, okay? So this one's symmetric, and it has a lot of features that will be optimized away by the compiler if you don't use them. It has an implementation that is succinct and therefore maybe not as super obvious unless you walk through it like I just did, and be very careful about how you're thinking about all these things and what order everything happens, especially the fact that you do this followed by asking what its value is. Remember, this happens at the end of the execution of this block, logically speaking, not in the order in which you see it, okay? Giving you something to think about a little bit when you're looking at other people's code. Everyone has their own style, all right? So that's a pretty nice generic synchronizer for mechanical buttons pressed by hand. I suppose some crazy gamer might think I can be 10 nanoseconds faster if I modify the circuit so that my falling edge goes out immediately, and then we hold off on the rising edge later on so that when I press my buttons, the computer knows about it before somebody else whose synchronizer works by delaying symmetrically on the falling as well as the rising edge, right? That might be a thing. I don't know. They also might remove their synchronizer or some gates out of it to shave off a couple clock periods there as well. Not sure that that's going to make a difference with your with your gameplay when you're down to that many nanos, or that few nanos, I should say. But you never know, okay? Other circuitry that's running at high speed, serial data with bounces. Sometimes you might do this to get rid of like I said, a single little glitch that might come in on the wire due to some, electromagnetic interference or crosstalk or something like that. That could also happen. You do not want a false trigger in that particular situation. This, for example, if this just happened and then nothing, and this is what, 100 microseconds? That's very small. You didn't press it and release it that fast. No human could do it that fast. That would be if it went high and stayed there, and this wasn't over here. That's my point. In that case, you want to use this to actually remove that completely. It would be operating as a low-pass filter, and the debouncer that's symmetric and waits until it's stable before it changes the output of the debouncer would eliminate this, okay? So it really depends on the noise in your system, depends on how long you're willing to tolerate waiting for the synchronizer, or rather the debouncer, to decide that it has been stable long enough to propagate it through and so on, all right? And if you wander around the internet, you're going to see, again, as many styles as there are people, and judge it both by opinion and the specific need of the circuit that somebody might have created. And the circuit is usually, in this case, I'm referring to what goes on over here that feeds into this whole thing, because it's the nature of this and the noise that comes in that you really got to decide is meaningful, or whether your solution is appropriate to address that need. All right? So thanks for watching. We'll see this in real action as we move forward in other projects on my channel. We got synchronizers, we got button debouncers, and finally we can generate signals that are clean from mechanical buttons, and we can do some cool stuff. I hope this was useful. Thanks for watching. I'll see you next time.